Hello and welcome to this episode of Off the Track. Today I'm joined by Corey Crain from Iota,
Oh, hi.
George Stoner from Evolve UK,
Hi.
and Jesse Stevens from Infinitude,
Ahoy, hoy.
Lachlan Lachlan George, and Lachlan Voss.
Hey.
Hello.
And the last two are currently competing in the World Finals 2020 season. So guys, do you want to just give us a quick overview of your team and what you're doing?
So we're both from Frontier Racing. It's our school's first time in the F1 schools competition. So we were state champions in New South Wales. We went through to nationals, came fourth. We're collaborating with Edge Performance, going through to the 2020 World Finals, whenever that ended up happening.
Yeah, that is an interesting topic that we discussed in one of our last episodes. So today we'll be doing an episode on engineering, as much was requested by our listeners, and so we figured we'd start out by discussing the wheel system. Now, what do you think is the most important part of a wheel system, guys?
I mean, the purpose of you're trying to get a wheel that's supported well, so you can have minimal sort of vibrations or movements while still having low enough friction that you can get a fast car.
I would say it's very hard to pinpoint. I think there's two main areas. I think stability and friction are like the two keys, and I'd like to hear George's opinion on that.
Yeah, well, one of the big things we focused on was reducing friction between the wheel and the track surface. So that was one of our big aims, as well as creating a light but still rigid wheel. Those were what we saw as our priorities during our wheel development.
Okay, and how did you go about that process of evaluating wheels and that kind of thing?
So I mean, we've been doing the competition for several years, and so we had experience coming up with different designs. And at the national finals, we'd used a wheel with an outside rim made of PTFE, supported by an inner wheel of 3D printed ABS. And what we liked about that wheel was we got very low friction characteristics from it. But PTFE is actually a really horrible material to use. It's really heavy and not very rigid. So what we did was, for the World Finals, we looked at developing with different materials. So materials infused with PTFE, as well as PTFE coatings on plastic and aluminium wheels. And what we found to be the best in the end was acetyl plastic infused with PTFE.
Right, and how did you come to that conclusion? Did you put them on cars and test them on cars, or?
Yeah, pretty much. We just ran as many physical tests as we could with all the different materials that we could get our hands on to try out, and the different sort of manufacturing processes, from using a CNC lathe to 3D printing the wheels. So I think one of the best things to do when designing a wheel is do lots of physical testing, is my main advice.
Are there any physical testing ways you can physically test a wheel other than putting it on a car and running it down a track? Any less time-consuming ways, maybe? Something like that?
Well, I mean, you can do tests where you can test the frictional properties of different materials using sort of blocks of material and dragging them across a surface. But I think because we had the resources to use a track, that's what we focused on, because in the end, running an actual race simulation is going to be the most effective way of coming up with a wheel design that will work in the real race.
Yes, George has a very good point there. Using a block uses the kinetic, like say you're sliding a block on a surface, that uses the kinetic friction coefficient of a material, and that's actually not what is used during most of the race when the wheels are up to speed. When the wheels are up to speed, it's static friction because the contact patch is always staying still relative to the ground. So using a sliding block on a surface isn't always the best test, but as George said, like race simulations is always the best way to do it.
Another aspect to keep in mind really with the wheels is because of the it's a rotating body, so it's going to have rotational inertia. So you're trying to minimize the weight, especially towards the outer rim of the wheel, because the rotational inertia of the wheel is proportionate to the radius squared. So by minimizing, especially at the rim of the wheel, you're going to be improving how quickly they can accelerate, which is a pretty big deal.
And so, is that one of the reasons that aluminium wasn't as good a material, George?
Actually, the main reason we didn't go for aluminium was because it damaged really easily, so it would permanently deform. So we had wheels that we worked with our sponsor BAE Systems, who are a large engineering firm, to make our wheels, and they could make us wheels that were down to 0.2 of a millimeter thick, and we could have aluminium wheels that weighed 0.6 of a gram, but they just didn't survive. They just crumbled. I mean, even putting the car down on a surface, you could damage a wheel.
Right, it's like aluminium foil.
Them. Yeah, we basically had aluminium foil wheels, and they were amazingly fast, but wouldn't last more than one run.
Right.
Would there be a reason why you wouldn't thicken them up, or did the weight become too much of a penalty?
We did thicken them up, and they were to the point where they were stronger and they could survive the racing. But we were just worried that we found that they had similar performance in the end to plastic, which to the acetyl plastic that we had infused with PTFE, and those wheels weren't getting damaged, so they were just the obvious choice for us because they weren't getting damaged, and we didn't want to turn up with a car with non-round wheels totally crumbled when we submitted our car.
On that point, is it a requirement that the wheels be round? I know it's a requirement they must turn in the rules, but do they need to be round?
No, but yes, make your wheels round.
I mean, did you guys ever consider making not round wheels?
As a joke, maybe, but
Oh, okay, all right.
Yeah, no, more usually the end result of a faulty manufacturing process that ends up with faulty wheels not being perfectly cylindrical, more than deliberate actions at least.
Right, okay.
With the minimum 26 mil diameter, if you were to create a wheel that's not round, you'd have to fulfill that the entire way around. So you'd be concerned, like if you were to make it so that it wasn't round, you'd have a wheel that's ends up being even heavier and bigger than, and plus you'd have to worry about vibration and whatnot, which is going to lose energy.
Because I know they added to the regulations, I think it was back in 2014 in Australia, that the wheels must turn. Because people were making wheel systems that would just lock up. Why was that a good idea?
Okay,
or when did they think it was a good idea?
Sorry, this is where my dynamics brain comes into it. Effectively, the coefficient of friction, there's two values. There's a static coefficient of friction, which is the highest amount of friction a surface can create when it's not moving. So it's like two forces holding against each other when they're both static. And then there's a kinetic friction value, which is when a surface is effectively skidding across, or they're sliding across each other. And the sliding coefficient of friction is a lot lower, or always lower than the maximum static friction. So by not rotating the wheels, you're actually sliding the wheels across the track, and hence it's a kinetic coefficient of friction rather than a static coefficient of friction. So you're actually saving the friction that your system is generating by being in contact, or the max friction. But yeah, it's not worth it.
Yeah, it's not something that you can implement these days, but it certainly was done back in the day. Oh god, a good 6 years ago now, 7 years ago. So we talked about how we tried different materials and that kind of thing. In terms of, obviously the wheels are important, but there's also a whole host of different wheel support systems, and I know there's you've got bearings, and then there's the so often thrown around like maglev type of design for wheels that everyone seems to dream up and then abandon very quickly. So do you guys have any thoughts on that kind of stuff?
So I think maglevs should just be thrown in the bin instantly. It's never going to work, especially on this scale. Please do not try and... A lot of people at very high companies are trying to work on maglev suspension in their cars and on railways, and it doesn't work. Please don't think as a high school engineer you're going to be able to do it. I'm going to pass over to George and he can talk more about the different kind of ways you can mount it, and then I'll add any thoughts to that.
Yeah, I mean, I think the first major differentiation about how you're going to run your wheels is whether you're going to have a shared axle for both wheels, so whether they'll spin together or whether you'll have wheels that can spin independently. I think we've always found that you want independently spinning wheels. And then also the other thing you can think about is whether you want how many bearings you're going to have in each wheel, if they're supported independently, because if you have more bearings, you'll increase the resistance to the wheel, to the rotation of the wheel, but also you might stop the wheel wobbling. And then also whether you want your bearings supporting the wheel on the outside, as we did, or whether you want the bearing in the middle of the wheel with a sort of a spoke design, and then having sort of hubcaps that you put on the end to fill in to sort of improve the aerodynamics. Those would be, I think, that would be my overview of the most wheel systems.
Yeah, just to expand on that, for our final car for the World Finals, we actually used a solid carbon fiber axle with independently spinning wheels with their own bearing, mounted in the middle with the spoke design that George spoke of. And essentially, while you do notice a slight decrease in the aerodynamics of the car in terms of disturbance in the the channel and the underbody of the car, the amount of accuracy and concentricity that we could achieve with mounting our wheels with that single axle, along with the additional strength that we could get from the carbon fiber, we actually found to be quite effective.
Well, that's very interesting you say, because I tend to both agree and disagree with both wheel systems. At Brighton, and Michael can abide by this, we had a wheel system where it was very tried, very successful when done correctly. So we had pretty much like a rotating axle with 2 full ceramic bearings, which are the lowest friction bearings that we really use in this competition. And I don't think, George, did you use hybrid ceramic bearings in your car?
Yeah, we used hybrid ceramic. We just had this sort of set of bearings that we, over the years, found to be the best set that we could, and we carried on with them. But they were hybrid ceramic rather than full ceramic.
So the full ceramic bearings have a slightly better frictional properties. Well, I think they're quite a lot better, but they break so easily. So our problem is that we could get wheel systems that were really good, but you had to try and align an axle, 2 bearings, and 2 wheels into one system. And with really fragile bearings, putting everything together ended up wasting a lot of systems, or in the case of Michael's team, impacting the car performance.
We actually found 3 different sort of issues with using the full ceramic bearings. Firstly, as Jesse mentioned, they were quite fragile and could be quite easily broken. Secondly, they were a fair bit more expensive than what you could find equal ABEC rating ceramic hybrids, which, if you've got the money, sure, but if not, they can be a really cost-effective way of getting a very good bearing. But also, thirdly, we found that it was a lot easier and a lot more efficient to be able to find the bearings in the smaller diameter, both internal and external, in the ceramic hybrids, thus reducing the rotational inertia of the wheel.
Well, the one thing that I would say to that is that we could have our bearings, the rotating surface was the inside, not the outside. So it ended up that we were only rotating 3 mil away from the center. So it wasn't terrible from that regard. But I will say that I would advise any teams going in the future, really think before you go about using full ceramic bearings. We wasted a lot of time, money, and effort trying to get them working, and only just got them working in the end. I think out of the 24 that we ordered, we got 4 that worked, or 8 that worked.
So you mentioned that Precision had some issues with the wheel system. I don't remember. I remember there being something about the wheel system that was a big issue, but it wasn't really my department at that time. So what was the issue with ours?
So I think the 2 main issues with yours, and a lot of teams in general, is the assembly process of a wheel system. I'll pass the question on to the engineers in a second. Of like assembling a wheel system is probably the most important part of it. It doesn't matter how good your design is if it's not straight, if it's not concentric, if it starts to track, if it starts to wobble, it's terrible and it won't work too well on the track. Whereas if you spent the time and effort trying to assemble it correctly, and regardless of it, whether you've got the really fragile full ceramic bearings or even the hybrid ceramics or even full steels, it doesn't matter so much as long as you get it all together properly. You should still get rough performance or the best out of them, because a lot of systems don't reach their full potential just because they're terribly put together.
Okay, and so you mentioned that it was like, or I think it was George that mentioned that you can have an axle through the middle, or you can have independently turning wheels. I'm imagining from my side that an axle would help provide more stability to the wheel system and wouldn't allow so much wobble and that kind of thing. Okay, so what kind of ways are you looking at mounting wheels to the car? Because I've pulled up the Infinitude model in front of me here, and it looks like we've got, a 3D printed wheel support system which holds bearings in place, and then the wheels attach into those bearings.
So on the Infinitude car, we had a metal cross member, which is like the metal insert that goes into the car, and effectively we had a massive contact patch where we just glued it onto the car, and effectively our wheels were held on by the friction of the stuff and the glue. We found that to be an all right system. There'd be many things that would change with our wheel system and how you mount it. I think George probably have some interesting ways of mounting it.
Ours was really basic. Ours was, so we had 3D printed parts with axles that stuck out, and then the bearings and wheels just press fitted onto that and were held in place by their own force. It was quite a simple system, and we probably could have had a better one, but I think we spent most of our wheel development time working on the materials we used for the wheel.
It's definitely beneficial to have a friction fit system as opposed to something that involves glue, because if you can, if you arrive to the location and you suddenly discover that your bearings have seized up or something like that, if you have the ability to pull your wheels off in like a matter of seconds, as opposed to having to work your way through the glue, it's definitely beneficial. And also, if everything's friction fit, you don't have to worry about play, because everything's very accurate, and like all the mating surfaces are going to be exactly parallel and concentric.
Good point about the being able to change parts quickly, because we had spare wheels that we could take off and put back on really, really quickly if anything happened to the wheels. And also we did work with the wheel manufacturers to make sure, like we went through tens of wheels just to make sure we had exactly the right size that would always fit with the right pressure onto the bearings and not come off.
Well, you see, that's where we didn't do too well. And this is one of the things that we'd go back and change. We had a wheel system that once it was together, it was together. It would not come apart unless it broke. And our wheel system broke at the World Finals. Right before we broke the world record, it actually broke and a part came out. And the problem is that to repair the part, we had to get glue right next to the bearing. And to do that and get it to dry in a space of 2 minutes at the competition is just not something you want to have to be dealing with. We ended up not fixing it, and Gary just said that you could race without it. But it's stuff like that that can really lead to big problems.
Hey, you broke the world record with a broken wheel system?
Yes.
Right, nice.
I mean, functionally, our wheel system was exactly the same. It just had a part missing of it that held everything together. So we think that a lot of our performance issues later in the competition came from the breakage earlier on and not fixing it. But yeah, I think the next thing to maybe talk about would be what to actually focus on a wheel system. Because I think all of us have gone about it in a very different way. Like Corey, we've all got different wheel systems, and we've all probably got some kind of thoughts of how to do it better. Personally, I think that from the wheel system, the friction isn't as important as the stability. But that other people might have a different opinion to that.
Just on that, Jesse, I think you can have the most frictionless, lowest friction wheel system ever made. But if your wheels are not running, if they're not tracking right, if they're not concentric, you're going to have major issues on the track in terms of consistency with your racing. So I would agree with you there. Friction is definitely not everything, because if you don't have the other elements of the wheel systems together, it doesn't matter how frictionless the car is.
I know. A very good example of how important assembly is, I think, is the really bad wheels that we use in development class and junior class in I don't know what it's called in the UK. But
Development class.
so it's a development class everywhere. That's good. But the wheels that you get given that are like just spinning in a grommet and then you have to assemble it together, they show really well the impacts of assembly on the car performance. Now, obviously, it's a bit scaled up because the wheel system's extremely heavy and extremely bad, but it can kind of show maybe a tenth or two can be gained by just assembling your wheel system properly.
I'd say that once you reach a certain level with the bearings, like for example, if you get some half decent hybrid ceramic bearings, once you reach a certain level, the friction, the actual friction of the bearings becomes fairly insignificant compared to any losses that you get by having non-parallel wheels or really wobbly wheels or just poorly assembled wheel supports. So yeah, I think that for us, reducing weight was a priority and still is a priority. But yeah, obviously, as long as you've got some decent bearings, there is some benefit to be gained from lower friction. But yeah, as Jesse said, I think stability is probably one of the key issues.
With stability, our regional car wasn't very aligned well, so it would tend to veer off and hit the walls quite early on in the track. And all that energy lost would often be at least a tenth of a second.
Does it have enough movement, like freedom on the tetherline guide to get that far?
Yeah.
Yeah? I swear I've never seen it happen. I don't pay that much attention to them on the track, though.
At the center of the track, where the tension isn't as high as towards the edges, there is quite a bit of play. So you could have a car, if the alignment wasn't up to par, you do have cars that can hit the side of the track. It also depends a little bit on the diameter of the tether guides, but that's a completely different matter.
One thing that I would say as well is that a lot of people don't actually quality check the parts they get in. You'll get a lot of bearings that, or you'll get good and bad bearings in your set. Or we found that we got good and bad bearings. They weren't always that consistent. So you want to make sure that you're putting on roughly equal bearings rather than, like, it doesn't matter if you got you got 3 really good bearings. That worst bearing is going to be the thing that undoes you all because it's going to track to one corner. Or one corner is going to be rotating slower. It's better to have 4 wheels that don't turn as fast or 2 wheels that don't turn as fast, but your car actually goes straight. Well, that's in my opinion anyway.
Yeah, you're always going to be as strong as your weakest link, and that weakest link is going to affect you more if it's going to, take your car into the wall or something like that, like Lachlan said.
Yeah, and just on that, a great way to test, I guess, the quality and the functionality of your bearings can often be to spin them up to a certain, apply a certain amount of force. So you might be using an air compressor, or I've seen teams use, I've forgotten what they're called now.
We use a Dremel wheel.
Yeah, Dremel, yeah. And spin them up for a certain amount of time, and then take the force away and see how long they spin for and time them. And that way you can pick not only the ones that spin for the longest, which are clearly having the least amount of friction in the system, but pick 4 for a car that spin for roughly the same amount of time, which will improve, I guess, the accuracy and the tracking, as we were mentioning before.
Yes, but on that case, make sure that you're using the exact same wheel design, because increased spin time doesn't always necessarily mean increased or lower friction, because if you're changing the wheels or they're slightly different, you're increasing your rotational inertia. So
yeah, my bad. Just to clarify on that, just with the bearings, not specifically with wheels. So I've actually seen teams 3D print little sort of like fan blades that they attach just to the bearing, and they'll spin them up, and then just for the bearing, not so much in the wheel itself.
as long as everything is consistent between the tests, it doesn't matter a huge amount if the wheel design is slightly different to your final design, just as long as it's consistent between all the bearing tests. That's what matters, because if you've got an independent variable that's going to be affecting it, such as a slightly different wheel design with more weight, more wheel inertia, then that's going to affect the results quite significantly.
So I think one of the biggest things you can think about when you're testing your wheels is that you're applying your testing method consistently. It's just like doing your science experiments in class. You need to figure out what your systematic variables are and your random variables, and try and account for those as best as you can. Would I be right in saying that, guys?
Yeah.
Well, that's a more broader,
Absolutely.
like in everything you do.
Yeah.
Make sure that you've got one variable you're testing.
And it may take a while to get through all of your tests with anything because you're only able to change one variable at a time. But if you're changing two, you don't know what's affecting it, whether it's, because you used a bigger fan on this bearing, or because the bearing's faulty, or because you used, a bigger or a longer axle and it wasn't the same length and that kind of thing. So you're never sure how it's going to turn out if you're changing two variables at the same time. So yeah, just apply the scientific method to your tests, and make sure you note that down in your folio. So wheel system representation, the folio, I think, is something that teams should also consider. Do you guys have anything to add on that?
Well, I mean, I think the best thing that I could advise is don't just take up your page with a lot of pictures, talk about it a lot, and then have stuff to bring into your engineering interview, like all your tests. Having all your stuff in front of you that you've done to test is a lot better than having it in a book. So yeah, that's all I could really advise.
They say
that especially applies for World Finals. Definitely with your engineering interviews, they love you bringing in physical items that you can discuss and they can really get around. It really works.
Yeah, and
Yeah, for the-
they say a picture tells 1,000 words, but while it does, putting just a picture of your wheel system on your folio, like taking up a whole A3 page, not a good use of space. If you're going to have an image in your folio, it needs to be referenced in the text, and you need to be making use of that image. If you're making a one-off reference to an image, unless it's crucial that image be there, and then it really shouldn't be, because you're trying to get as much information across about your system as you can. And in my experience, it's difficult to cram all the information you need down into the, what is it now, 10-page engineering portfolio?
I think so. 10 plus a
10
cover.
I believe you.
Yeah, I think we dedicated a whole page to wheel design.
A whole spread, or just one
A whole
page?
1A3 side.
Right, yeah.
And that was going through talking about the development, and we documented each sort of material we tested, but also we have photographs of these, for example, the aluminium wheels that just failed. And also those were the types of objects that we had presented on a board that we took into the engineering judging, going, these are the wheels we tested. And for example, this is why we didn't use this wheel. Despite the fact it was very fast, it obviously wasn't suitable for actually using at the competition.
It's also, I would say, quite crucial that you record a lot of your testing, not just keep it in your locked away in your head, but to actually record it in a spreadsheet or something. Because even though you may not end up using it for your portfolios, it's good to have too much data than not enough data. So if you have, even if it's just like some preliminary tests, it's always good to have lots of data that you can discuss in your interviews and your portfolios, rather than just talking about qualitative stuff. You want to be talking about quantitative stuff, so exact numbers rather than just this was faster. You will say like by how much.
Yeah. And also we did a lot of sort of mathematical analysis, looking at sort of the distributions of data and saying we can say with this much certainty that this is actually a better design than this, because often you can get, because of canisters, you can get lots of spread with your data, and it can be quite hard to differentiate which design is better than another. So I would encourage teams to analyze their data and look at techniques for doing that.
And that's an area where spreadsheets are really useful, because you can get it to do all of your standard deviations, all of your means, all of that kind of stuff, C-scores, etc., for you, and it can present you with, a normal distribution, and it will show you all the data you need to know, and you don't need to sit through there with your Casio calculator crunching the numbers.
Yeah. On the topic of the variation of canister, on a very slight, sorry, this is a sidetrack and not about a wheel system, but when we were doing our loads testing, we launched a lot of cars, and when we got a lot of data for how inconsistent the car launches are and stuff like that, and it was actually very useful to put onto our next lot of testing, as George said, because you can say it with a certain amount of confidence. Well, we said that this would be the upper and lower limits of what our car's improvements would be because of this, or the upper and lower limits of our car performance with this system. So it was we were able to actually work out our factor of error because we'd actually made a model of how the canister had worked and how the canister had functioned in our car and how inconsistent the ones we were using were.
Okay, yeah. We weighed out all of our canisters to try and get some consistency. I know some of the inconsistency between the weights of the canisters will be due to the metal content, but also trying to get something better with trying to get more consistent with the gas. So I think we weighed out 1,000 canisters, and it was hours and hours and hours. But we divided them up so that we were using canisters of similar weights between. So for each variable we'd be testing, we'd be using canisters within a single weight bracket.
Did you just as a question, did you measure your canisters after you'd finished the test to get their afterweights to see how much gas was actually inside of them? I'd just be interested to know that.
I measured some of them. I can't remember how much gas was actually in them, but we did it just to check that measuring out the different weights in the first place was actually worth it to find the difference in the gas inside, rather than it's just a manufacturing variation with the metal. But I can't remember. I think it was something around 8 grams, but I can't remember what it was exactly.
Oh yeah, no. Because we just had a way of, so we had runs where our car was running a bit slower, and we weighed every canister after our run to see if there was like an outlying canister and our car like fluked it or something like that to make sure. So I mean, for some teams, if they've got the time to do it in their testing, I'd maybe advise recording weights before and after, but that's only my opinion.
Yeah, absolutely. I'll back that. We weighed all our canisters before and after, and I guess we had a certain tolerance, if you will, that we would accept, and anything outside of that we would just have to write off as a fail run, essentially, because it was outside of those brackets and couldn't be considered reliable and accurate data.
Unfortunately, there is also there tends to be some variation in the actual puncture size of the canister, which can have quite a significant effect. So, like any scientific test, it's worth just obviously you want to sort of remove the tests that obviously they didn't disperse enough gas or too much gas as per measuring before and after, but it's also just worth taking lots and lots and lots of runs because that gives you just lots of accurate data to work with, so you eliminate pretty much any random error and you lock it all down to a pretty reliable test.
And of course, put all of this data into your spreadsheet and make sure you analyze it properly, because it looks really good to the judges if you're taking this data, but then you have to go that step further and actually utilize the data, because otherwise, what's the point,
Okay, well, essentially, starting out, generally speaking, there are 2 different ways you can go for manufacturing a wheel. You can machine it using a lathe or a CNC, or both, as we did, or you can 3D print. For us, we went towards the machining processes rather than 3D printing. Just for us, accuracy and consistency, we found we could get it better with the lathing, but results may vary, different processes. So we went for a 2-step process. So we would actually turn down our wheels to size on the external and internal diameters of both the outer rim and the central bearing housing. And then we took that product and then placed it into a jig that we had engineered. We designed it and engineered it to be able to be put into a CNC and have the spokes of the wheel machined out. And we found that while it could be difficult and a bit time consuming at times, I must admit, we found that to be a really effective way of producing wheels that were quite accurate and quite thin as well.
I seem to remember our manufacturing process being similar to that. We put wheels like I don't remember the material, but we put material in a lathe and then a CNC lathe, and we lathe it out at a manufacturing company. Jesse, you actually probably know more about my own wheel system than I do.
Yes.
Yeah. So that's how we did it, wasn't it?
Yeah. So effectively,
It's PEEK, isn't it?
Yeah, polyethyl ethyl ketone. So effectively, what we did for our manufacturing processes was said we can't get the precision and accuracy that we want. So what we decided to do is we just outsourced our wheels. That was just because of the restrictions that we had. Because our machines our CNC lathes and our like manual lathes, we couldn't get anything within 0.5, let alone 0.1 that we wanted. So we reached out to various manufacturing like places and ended up settling on RC Williams, which was one of our local people that not just did our wheels, but also taught us a lot about how to manufacture that kind of thing for the future. And maybe reaching out to local manufacturing companies and just asking how you do things. And I mean, don't pester them, but like ask a few questions and learn about it. So maybe you could do it yourself, or maybe they would outsource it for you. I think that would be a good advice I'd have for you.
We used RC Williams as well. Their logo's all over our portfolio because they're a good local company, family business, I'm pretty sure as well. And yeah, they taught Jack and Ben a lot when manufacturing the wheels. And so we used very similar wheel systems from memory, didn't we, Jesse? Yours was
yeah, we
a
did.
bit different, yeah. The standard.
Well, ours was quite different.
Yeah, but same principles. I think probably, obviously, Corey's was quite different, and George, your wheel system was quite different, and you seem to have done a lot of research into your wheel system. So,
Yeah.
What kind of manufacturing processes did you use? Obviously, you work with BAA systems, so did that expand your manufacturing capability a lot as well?
Yeah, so previously we 3D printed our wheels, but with BAE systems, they had really accurate machinery that, I mean, when we got our wheels in the end, we couldn't, with any instruments that we had available at our school, measure the difference between the wheels. So they were really consistent, and also we could work with them, and they were really happy to manufacture loads of wheels for us, out of different materials and testing different thicknesses. And just sort of different design changes to the shape of the wheel. And so, yeah, so I mean, the side walls of our wheels we got down to less than 0.2 of a millimeter. And so if you hold them up to the light, you can see through them and stuff. And so we had really thin, and we worked with them a lot. And as you were talking about sort of learning from them, they taught us a lot about the manufacturing process. And we found it really helpful to work with them so we could better understand their manufacturing process, which allowed us to design a wheel, to design the best wheel we could that they could manufacture. So I think if you do outsource your wheels, it's really important to talk to the people who are going to make your wheels about how it will happen.
And some of them are really into this kind of thing. Like they're really proud of it, and they're really happy to explain things and show you things. I know this because it wasn't it wasn't a wheel manufacturing thing, but when we had a sponsor, Detpack, their international cardboard company, they produce all kinds of packaging for McDonald's, Burger King, Hungry Jack's, that kind of thing. And they did all of our posters and that kind of stuff and promotional materials. And so we went to see their team there, and they were just so enthusiastic about helping us as a team of students and showing us what they did and what they were capable of. And they were actually far more excited about us being students than customers, because I went back for another tour of the factory with McDonald's, and they were nowhere near as enthusiastic with the McDonald's team as they were with with us. So sometimes you can get really enthusiastic people who are really enthused to help students, learn and that kind of thing. And I think that's something that you saw there, wasn't it, George?
Yeah, no, that's definitely something we saw, and they were always really keen to help, and they would we'd have phone calls with them, and you could tell they were excited to be talking about what we wanted to do. And they were really helpful. And I think also one of the things we did was when we went into BA Systems and other sponsors is sort of have a positive attitude and be really sort of try and be engaging, which makes them sort of like you and sort of can help with getting sponsorship as well.
Yeah,
If
don't
they see you as,
Oh no, sorry, go on. Sorry, I interrupted.
sorry, if they see you as actively engaging students
and interested in their business as well.
Yeah.
So one of the things is that when you're trying to work with people and collaborate with people, you're trying to form a relationship. You're not just trying to get a service from people, because a lot of the people that are willing to help you out are actually interested in the thing you're doing and want to actually know a lot about it. The reason that it's a lot easier to get engineering people to help than, say, marketing sponsors or getting money into your program, because a lot of people are very interested in this kind of thing and just want to apply their knowledge or help you out in their way because they kind of enjoy it themselves. And it makes their life a bit more fun, and they'll enjoy passing on their knowledge because that's their the thing that got them probably into it, working with their parents or working with people or stuff like that. A lot of these people are doing jobs because they like them, and if you're allowing them to do a really good job or allowing them to have fun at their job while still doing their job, you're doing a really good, you're doing a service to them, and you can form a real good relationship off that. It's some of our sponsors I still visit and still have good chats to about our time back then, even though it's been 3 years and I haven't talked to them or haven't gotten any help from them for a while.
Yeah, I see this a lot with the Subs in Schools program we have in Australia. There are people that are genuinely really interested in the program. There's a guy, I can't remember his name, from ASE, and he comes down and he helps. And he's really passionate about the Subs in Schools program and really believes in it, And I've met quite a few of these people, and when you just explain the Subs in Schools program to people who are even slightly engineering minded, like other uni students who were doing engineering, I explained it to when I had classes with them, and they were super interested because it's getting kids into engineering, maths, and that in a fun and engaging way, So I think that's something that teams need to consider when they're trying to get help manufacturing their wheels or any part of their car or anything from companies, is you need to try and get them interested, So Lachlan and Voss, there you go. That's our sage advice for today. So thank you for listening to Off the Track. You can find the show on Apple Podcasts. You can rate us on there. Give us 5 stars if you'd like. It would really help. You can also find us on Twitter at Off the Track Pod or Instagram at Off the Track Podcast. Or you can visit us at offthetrack.net. Stay tuned for more episodes relating to engineering. We have plans to bring out more high quality engineering episodes. So yeah, please stay tuned. And if you have any questions about engineering or any part of the competition, you can send them to us on our social media.